Good afternoon, everyone. It is so good to have you today. Today we will study the topic of double series. So double series are like some kind of generalization of your regular series. You know that a series is an infinite summation of terms, and formally it is the limit of a sequence of sums, of finite summations. So with double series, we go further from that. And double series, you are basically summing an array, an infinite array, like I will show you right now. So we can write some term that is here, and then we go with this one, and then it goes to infinity. And this is pretty much, your regular series. But with double series, we go and add another row here. So here we have this, and we go on to have to add another one. It's infinite, and this also goes to infinity. So this is pretty much like an infinite matrix. So we are summing an infinite matrix, and the notation here is just this. So we have, let's say that your general term here will be A and K. So you will have this, and from 1 to infinity and to K1 to infinity. So a lot of interesting things happen with double series. We could ask if what happens if we sum, if we start summing like this in rows. So this produces some summation. If we fix the first term, the n as n equals 1, and we let k span its whole range, this will be some number, and this number, this is fixing n equal to 1. So this will be some number. Let's, what do you want to call this? Let's call it B1. And then when you sum the following row, you will have this with 2, and let k vary in its whole range. And this will be another number given that it is convergent, because some rows may be divergent, and even if some rows were divergent, it could be that if we sum in columns, the columns could be convergent. That there are a lot of things that happen. So, but for the sake of simplicity, let's call this B2, supposing that this is not infinite, supposing that all of those rows, of all of the summation of those rows are convergent. So this goes on, and in the general term we will have some bk, right? And then we can sum all of those numbers and get, so we sum all of those, and these supposing again that this converges, this will be some value, and that we may call the value of the double summation. So yeah, this is some value. But what happens if we sum on the other sense? So what happens if we sum now columns? So we sum columns. This is the value of the double series. Let's say starting or summing. Let's put it like row column. All right, and if we go column row, we will have a different scenario. Let's give some space here, and this will be now we will fix what? We'll fix the value of k here. So this is the column k equals to 1. So this will be a 1 in the second element, and we let n take all of its values, and this will be called, let's call it C1. Alright, and then the following column will be have, if we sum all of those terms, we'll have this, which is another number, and so on. So if we sum all of these numbers, if we make this summation, let's give some more room there. If we make this sum, this will be another value of course of the double series, but column row, because this is the order, you know. We first calculate the columns and then calculate or add all of those numbers. And so yeah, these two numbers may be different, could be equal, could be different. Some of those could be divergent, could be infinity, the other one could be finite, or could be convergent, I mean. So a lot of things happen, lot of things. So this is the general case. In the general case, everything can happen. But when we go to some particular cases, to some particular under some particular conditions, we can get some result that most desirable result that these two values are equal. So we will now see in which conditions it doesn't matter if you start calculating the rows or the columns, the values will be equal. So let's do that. So let's put an let's call this a theorem, or first theorem, theorem 1, and let's write down the conditions. Alright, so if we fix n, if we fix n, then the series letting k range over its full span is convergent, and so we are assuming that this is convergent, you know. This is like when we were fixing n here, we are fixing n here, fix n. So we are under this case, supposing that all of those b values are not infinite. So we are under that condition. And moreover, we will suppose that this function from the naturals to R defined as follows. So this is pretty much a finite summation until the kth term. Alright, so we have that function, and we say that the series converges uniformly on n. So this is another, let me write this. So this is our first hypothesis, that if we sum in rows, if we start in some rows, then those values are, the summation of the rows is finite, always finite, is convergent. The second assumption is that when we define this function for every n, then the series converges uniformly on n. So this is uniform convergence, right? Then now there comes the good part. Then it happens that, let me add some space. All right, so that happens, and so I will not give the full proof of this here, but I just will tell you that this is a property of sequence of functions. So this falls under the theory of sequence of functions. Because here we have this. This is a very heavy assumption that theory is uniformly convergent, and so under these conditions we will have the desired equality. But now you may wonder what is the meaning of that? What means that some series converges uniformly? Well, and I mean, moreover, that series is the finite summation. So what's happening here? Well, if you try to understand a little of what's happening here, you'll see that. Let me have some page. Alright, so Fn is a function that pretty much can, let me just put it here. So f sub n is a function that given some value of k, will have the kth summation of the series fixing the value of n. You know, this is fixed. So whenever for every value of k we have the definition, and when k goes to infinity we will have so if we write it here, no, I mean the limit. This is equal to alright. So this is what's happening here. So we have this limit, this summation, and then we have uniform convergence. So with uniform convergence we are allowed to do some kind of tricks. We will be allowed to get inside of some summations. I mean, the limit can enter the summation symbol, you know. So this is basically what is happening. So we have this summation, and we can apply the limit here, and the limit will be into it, and this is pretty much how this thing works. But as I told you, the fact that this is uniformly convergent is heavy. This is heavy. So by all means, this is not a general property, and I want to end this video by showing you explicitly one double series that doesn't hold this property. So let's go into it. We can do it with some imagination, but there is a pretty kind of famous example, the standard example of how the summation can be different. I mean, the general case is the following. So we'll have rows that at 0, if you sum all of the rows, the value will be 0, and on columns we have this value here. So we'll be moving one block at a time. The summation is 0, and then this will be 7/8. So you see what's the pattern here, right? So this is -1, -1, -1, -1. And the value of the rows is always 0. What happens with the columns? Well, with the columns, the summation here is a half, and the second case is a quarter, and the third case is 1/8, and so on. So for the following, given that we will give here 15 16th, the value will be a 16th. All right. So obviously this summation is not 0. I mean, when we sum, this is the value of the summation of the columns, and when we sum all of those values, you know, this is, let me write it here, this is a half, and this is a half square, this is a half cube, this is a half fourth, and so on. So this is a geometric series, and its value is 1. And on the other hand, when we sum all of the rows and you sum all of those results, the value will be 0. So given that 0 is not equal to 1, then this is not, in this case, summing rows or columns and columns and rows is not equal. So why is it that our theorem didn't hold here? At first, it is obvious that the first assumption did hold because it is convergent, because when you sum over, this is fixing n, so fixing n is summing rows, so everything is 0, so it is convergent, so this did hold. But what failed to be realized is the second assumption. When you define those functions, it's that series is not uniformly convergent, so that's what's happening. So even with this relatively simple, really simple double series, we won't have that property to be true. So yeah, this is it for today. If you're interested in this, and of course we can go further. I mean, we could go with triple summations, and this is ANKR, and so on. So you won't have an array like this, but a 3-dimensional array, and that could be interesting to analyze in some cases. I mean, some physical cases perhaps. A physicist may be interested on that, and this can be easily generalized. So yeah, this is it for today. If you have any questions or you want me to cover another topic that you're interested into, you can put it down in the comments. As always, please hit the like button and please subscribe. So see you around in the next video.